Hello, this is Dr. Flight, and I'm going to do a little video here that goes through another example of regression. This time I'm going to use a different data set, and we're going to use um, some composite variables that were formed from a factor analysis. So this is going to be the automobile data. Now, in other videos, I did a factor analysis illustration, and I kind of walked through the factor analysis process where it can get messy and it can get a little challenging. So you need to spend a lot of time just doing it, basically. And I went through this data set a couple times, two or three times at least, and I came up with a 9-factor solution. So I went ahead and did that in advance just so that I would have it here. And so we have our data set, and this is it. And remember, we have all kinds of variables that deal with like emotional attachment, social recognition, identity signaling, word of mouth, switching, satisfaction, all kinds of stuff. So I actually developed a 9-factor solution that was what I ended up settling on. So if we go to dimension reduction and if we go to factor, again, I went through a lot of work to get to this, but I've got a 9-factor solution that I'm happy with. So you can do the anti-image, you can do the KMO test and all of that stuff. The extraction method, I forced a 9-factor solution because I felt like that was appropriate after doing, again, a whole bunch of work on it. I use, as you know, a Promax rotation so that the factors will share variance with each other. So that it's an oblique rotation. The scores, I'm not going to save scores right now. I'm not going to do this. We're okay. Or actually take this off. I don't need that either. Options, I do want to show you this. You can do exclude list-wise. I don't necessarily like to eliminate data if I don't want to, so I don't want to do a pairwise deletion. In fact, what I'm going to do is I'm going to do a replace with mean. I do this fairly often if I feel like the data is not random, it is randomly missing if it is missing at all. So mcar would be the deal, or mar, missing at random. And I feel like we're okay with that. I am going to sort by size. I am going to take away little coefficients in the table so that I don't get too confused, okay? So this is the data, and these are the variables that I've used. If you want to practice this, you can practice this. So go ahead and bring these variables over if you want to. And just pause this, and in your SPSS go ahead and bring these over. If you're doing this at home, no problem. I'm going to go ahead and run OK though, so that we can take a look at what the results are. So again, the Bartlett's test, KMO, Kaiser, Meyer, Olkin, MSA is perfectly good, and we've looked at this before, so I'm not going to go over this again. I'm going to jump right down. We've got the commonalities going on. We've got, so I specified a 9-factor solution. As it turns out, these last two factors only have 2 variables in them each. But knowing what the data is, knowing what the survey says, I am convinced that these should be factors, even though it is against the eigenvalue greater than 1 rule of thumb. I don't buy it this time around. So again, this is a gray area where researcher discretion needs to guide some of this here. So I'm going to drop down to the pattern matrix, which is what we want to look at in a Promax rotation or an oblique rotation. And we have, again, 9 factors, and we have the variables here that load onto each of these 9 factors. Okay, so that's the way it breaks down. You'll see no cross loadings. You'll see all of these are fairly high. The lowest is 0.75 there, 0.33, 0.47. So these are all. We have a 0.659. If any of these, this is a little odd or weak in terms of the loadings. So is this one, because we go from 0.933 all the way down to 0.662. So those may be a bit weaker, but I'm still holding them together. And here's one of the reasons why. For each one of these factors, we need to measure the Cronbach's alpha. So like for instance on this one here, where I even think it's a little weaker, we'll go to analyze, then scale, then reliability, and then I'm going to go and I'm going to put what these items were here. These items were brand elevates my sense of pride. So elevates my sense of pride, enhances my confidence, and my sense of self-respect. I'm going to do OK. And my Cronbach alpha is 0.877. 0.70 is the cutoff that I use, and most serious researchers would not run a factor with anything less than that. So even my weaker factors here still have a strong Cronbach's alpha. Now I'll make this point again. You want at least 3 variables. These last 2 factors only have 2. So we use just the simple correlation between these guys. That's what you should report for this in terms of reliability. And these last 2, it may be why the eigenvalues are relatively low. That could be the cause of that there. So anywho, we're good. This is what we want to see. So what I want to do next is I want to create composite values for these. So this first one is going to be the emotionally attached. Okay, emotional attachment. That's what I'm going to run here. So I'm going to transform compute, and I'm going to do emo att average. Okay, so basically what I'm saying here is that this is the emotional attachment average. No, I'm going to do a mean composite score. So I'm simply going to average together each respondent's score on the 4 variables that relate to this factor. So we're going to do mean, and then the 4 items is I am emotionally attached, 1. I have a sense of belonging. That's the second one. The third one is I feel loyal. And the fourth one is I would expend effort. There we go, number 4. Now, where did these come from? They came from our factor scores, our factors right here. These are the 4 factors, the items that load on factor 1. So these are the 4 items I'm going to take the average of to form a composite score. So I'll do OK, and then I'm going to do boom. I'm just going to show you here. We got our variable view. We created a new variable here called emotional attachment average. Also, I'm just going to do this real quick. Let's look at, we're going to explore. Let's explore this variable. This is a new variable we created. Let's explore. Let's do plots. Let's do a histogram. We can do a normality plot test as well, and we can do okie dokie. So we have our information here. We can go ahead and divide and look at these skewness and kurtosis scores. Test for normality. Now look, the Shapiro-Wilk is still 0, which says that this is not normally distributed. And if you look at the histogram, you have all of these plopped over here at 1. But if you, in general, look at this, if we ignore that, which may be some form of an anomaly, This is pretty normally distributed except for those one scores that are there. So what happened? Maybe people entered zero, maybe people, I don't know what they did, but for some reason they threw in a zero there. Now, this is actually better data than we had before when we had the individual variables, and we say this little blip here. So that's a, kind of an issue, question mark there. So even though we don't have normality, we have a big sample size, and we have something other than this number one here that approaches normality. So, and it'll be this, it'll come up here as an issue. We'll clearly be able to see something going on. But at any rate, I'm not going to lose a whole lot of sleep over that. I'm going to keep that there. So my job now is I created a composite variable here. You can also use these loadings to weight the scores appropriately based on these loadings, because these are standardized. So you can use these as weights and use these as a weighted score to also create a composite score as well. There's also another option. Actually, SPSS will create a score for you as well. So there's a couple different options. And so if you go into Analyze, if we do our data reduction, we do a factor analysis here. If we click on scores and we use save as variables, we can actually, this will allow SPSS to create a factor score. It'll do it all automatically for us. It'll create, so actually let's do this. Okay, let's just do this. It will, I just did that, and I'll run this, and now let's look at our data. And what we have now is actually going to be 9 new. So this is the one we created, which was the average composite. This is going to create, using another weight system, a weighting of the factor loadings, 9 new variables, 1 for each factor. So we could use that as well, and we could actually analyze. This data may be a little bit better for us to be able to use. I don't know, we'll just look at this. So this is, again, the emotional attachment score from the data that was created by SPSS. And we still have a little bit of an issue here going on there. Our test for normality is still not quite there. So we're going to have similar data resulting. Yikes, a little bit of issue, a lot of issue going on there. But that's another way we can get our scores. I will typically take an average here. That's what a lot of people do. A lot of researchers will do that, but you can have researchers argue, and you can look more into the different various methods of doing this if you want. So what I'm going to do is I'm actually going to clear these because I just don't want those in there right now. And I'm going to go ahead and create a composite score for some of these other factors. I'm not going to do compulsive buying, but I am going to transform, and I'm going to compute, and I'm going to create some other ones. So the social recognition average, social recognition is the one I'm going to do. And I'm going to go ahead and do this. I'm going to pause the video while I do this to save a little bit of time. And when I come back, I'll have all the variables done with new composites for you to see. Okay, we've gone ahead and created composite scores. And again, these are means, so the mean scores. And so what I did was I took emotional attachment, social recognition, satisfaction, identity signaling for the brand, esteem, self-esteem building, and then trust and faith. So I actually, out of the 9 factors, I went ahead and just created composite scores for 6 of the factors. And I'd want to do this for all 9, but I'm only doing it for 6 now. What I want to do is predict word of mouth, or what I want to do is predict intention to buy. So I'm going to go to Analyze, and then I'm going to go to Regression and Linear, and I'm going to do my intention to buy, and I'm going to add my variables in. Now, some of them I already added in, so I need to add these others here that I didn't have. So emotional, social, satisfaction, identity, esteem, and trust and faith. Some of the others, word of mouth. I'm not sure word of mouth predicts intention to buy. So again, there's causality we're suggesting here, and I don't think because somebody is willing to give word of mouth, they're necessarily intending to buy. So, so now word of mouth may be a dependent variable, and so we might use it as a DV, but probably not an IV in this particular case, nor is compulsive buying tendency. That's not somebody, compulsive buying tendency will probably not be something I would theorize as something that would predict or lead or cause intention to buy or to purchase. Okay, so we have here our what we're going to do. We're going to have a model fit. We're going to do estimates. We're going to do case-wise diagnostics, 3 or 2 or 2.5 standard deviations, depending on how strict you want this to be, is what we're going to do there. Descriptives, partial, part and partial correlations, then collinearity diagnostics. Plots, we're going to have a histogram, or we're going to have the normal probability plot, and then we'll also look at, these will be a little weird because our scales are not very large. We only had 5-point scales, so these are going to be based on a 5-point points that we have. Save, Mahalanobis, and Cooks, we'll do those guys. They seem pretty awesome. So we'll keep that like that. Options, we're not going to worry about anything on options, style, bootstrap. I think that's what we want. I think that's about what we want to do. So we're going to run this. We're going to look at this, and we have our mean standard deviations for our descriptive statistics. We have a sample size of 450. Let's look at this. Intention to buy, and then we have our variables. So we're looking for a large variable, large R's here. Okay, these aren't like super big. Social recognition is small. So there's something going on there that we might be concerned with. Also, esteem is small. We might have a problem with that. Some of these others are pretty large though. So we're looking for large correlations, but then we're looking for small inter-item independent variable correlations. So we would want these to be small. So these emotional attachment ones are fairly robust across the basis here, but not super high. The 6.5 is a little bit of a big hit right there. So esteem and social recognition, that, well, you would expect those two to go be high. Those are there. All right, nothing else really jumps out at me at anything above a 0.6 or so, or really too great. But there is some inter-item correlation, so we've got to look at that a little bit closer. We're going to jump down here actually and look at the tolerance. So all of these tolerances are above 0.1, okay, and all of these VIFs are below 10. So there's no indication here of severe multicollinearity. Although I do think there's a little something going on, because this is really, when we have some really low social rec and esteem, what's probably going to happen is we're probably going to see that these don't contribute a lot to the model. That'd be my guess. There may not be collinearity going on, but they might just not be very good predictive values. And actually, we look at the model fit. We look at a 607, which is fine. I mean, it's not like super great, but it's not bad. I mean, a 0.6R is good. But then when we look at the adjusted R square, it almost cuts in half. At least by a third or so, it gets cut when we go from 0.607 down to 0.3 6. So there's some double dipping here that is being accounted for, and it detracts from our overall fit. Now the model fit, the F statistic, of course, is going to be significant, but that again doesn't really tell us a lot. It just means the overall model is fit. Okay, so other things that we would look at this normality plot. Again, we've got a bit of an issue with normality going on here, and some of the variables may be problematic from a normal distribution issue. We've got that going on. The other thing that we have here, remember we wanted about, I think this measured a 3 standard deviation issue. So if we did a box here where we looked at 3 standard deviations, we see some points here that are outside of where maybe a 3 would be. So that tells me that there's probably some outliers in the data here as well that we may consider dropping out. We may consider getting rid of. So we've got that going on. We come up here, there's actually a box here that says case-wise diagnostics if you have potential outliers. So we have 5 cases that we could consider dropping because their residuals are greater than what we would expect. They're outside of the 3 standard deviations that were, so these guys that were outliers that were outside of this predicted value, from away from the mean, would be the problem ones. So we could consider taking those off. The other issue with outliers would be the Mahalanobis distance and Cook's distance. So the Cook's distance is low. We're not worried. So we look at the minimums and the maximums here. But the Mahalanobis distance measures here 30.882. And again, we had what, 6 degrees of freedom, I think? Was it 6? Yeah, we had 6 independent variables, so we have 6 degrees of freedom. The largest is a 30. So if we divided 30.882 divided by our degrees of freedom 6, that's 5.15. Okay, remember the cutoff is 3 to 4 if it's a large sample, 2.5 if it's small. So that's clearly large. So that tells us there's some data, there are some observations that are beyond normal. They're outliers. So what we do is we, let's see if did we ask for, when we ran this, we asked for the Mahalanobis distance, right? And actually we don't need this. This is extra. We didn't need that. With the Mahalanobis distance, so what we do is we sort the variables by the Mahalanobis distance. We're going to do it in descending order. We're going to do OK, or we're going to look at this data. So these guys here are potential outliers. This is what we want to. We probably want to delete them or get rid of them. Again, not a big fan of deleting data, but that might be something we want to do. So let's go here and calculate this again. If we used 4 as our cutoff, and we have 6, let's see, 6 times 4, and we have 6 independent variables, then 24, these guys, whoops, I think it was the first 6. These guys here are going to be outliers. All right, so I'm going to do something that I don't normally do for brevity here. I'm going to take them out. I'm going to take these outliers out. Boom. Now that's scary because I just deleted some data. Now I'm going to save this. I may save this as a new file, without outliers. That'll probably be what I'm going to do. But before I do all that, I'm going to go ahead and I'm going to run this regression again. And this time again, I'm looking at, I've got residuals saved. I've got options. Nope, I'm not going to worry about options. Statistics, case-wise, outliers, okay. I'm just going to continue like this. Cooks. Okay. All right, I'm going to shoot that okay again. Now I'm going to come down here. I'm going to look at my residuals again. Mahalanobis distance. I've still got some outliers going in there, and I've also still got these cases. So maybe I'm going to find 50, 66, 38, 409, 436. Now these should be based on my row numbers. So 50, 66. But I tell you what, I'm just gonna leave it the way it is. We could continue to delete these, but just so that I don't get too crazy here, I'm just gonna keep it the way it is when we eliminate these. Okay, so this means then I have my coefficients. I'm going to look at these guys now. I've looked at my variance and inflation factors. I looked at all those already. I'm looking at these standardized coefficients, and I'm looking at significance. Look at how small emotional is. We knew that was going to be small. Look at how small esteem is. We knew that was going to be small. We see that esteem is not significant. We see that emotional attachment is significant. I'm going to take esteem out, and I'm going to see how that influences our adjusted R squared and our R. It won't help. I mean, whenever you take variables out, this goes down, but I'm looking at to see this difference and see how much it goes down. So 359 is what we have, and we're going to take esteem out to make this a better model. So we're going to take esteem out of there. Taking esteem out of there, we're going to look at this. 359, our adjusted R squared did not change at all. Our R went down just a little fraction, but nothing to worry about. We still have a significant model, and you know, things are still looking good. Now, emotional attachment, again, it does not contribute very much. We look at the part correlations. If we squared that, we will know the degree, the variance that is being provided, and it's extremely small. So emo attachment is another variable that we can take out, and it's not going to negatively impact our model very much. Okay, we're going to take that bad boy out of there. And so we take it out again, didn't drop our R's hardly at all, yet we still have a fitting model. Okay, so that's where we are. That's how we're going to do this. That kind of takes you through another example of a regression type model. Thank you very much. Again, if you guys have questions, shoot me an email, touch base with me or whatnot, and let me know how things are going. Thanks.